This paper presents a method for riggable 3D face reconstruction from monocular RGB images. Given monocular RGB inputs, our method jointly estimates a personalized face rig and per-image parameters, including expressions, poses, and illuminations. By applying the per-image parameters to the rig, we can obtain the per-image reconstructions. The rig can also be animated by other identities, achieving face retargeting. Riggable 3D face reconstruction has applications in various fields such as movie, game, and telepresence. Traditionally, the reconstruction is obtained by various optimization constrained by handcrafted priors and linear face models. These methods usually suffer from limited face model capacity, inefficiency, fragile pipelines, or require manual intervention. Recently, deep learning approaches demonstrate great potentials in addressing these issues. Nevertheless, these methods mainly focus on static reconstructions and fail to produce personalized face rigs. Very recently, people proposed to use neural networks for regressing blend shape rigs from monocular images. However, their estimated 3D geometry has unsatisfiable quality. Our key idea to address these issues is to integrate deep learning and optimization when reconstructing face rigs. Following this idea, we propose an end-to-end trainable network embedded with a differentiable in-network optimization. We first represent the reconstructions with some parameters decoded by a neural network. Then, the learnable in-network optimization is integrated to iteratively solve the parameters based on the first principle constraints, including feature metric multiview consistency, landmark alignment, and photometric reconstruction. The in-network optimization explicitly enforces constraints governed by the first principles. Therefore, it better leverages the nature of the problem, achieving more accurate geometry estimations than previous direct regressions. On the other hand, the learned neural modules leverage deep priors to constrain the yield-postness and ease the hardness of the optimization, making our pipeline more efficient and robust than traditional optimization. More specifically, our method contains two modules. One is the face rig parameterization, the other is the learnable optimization. For face rig parameterization, we use a neural decoder conditioned on the input images to parameterize the face rig into a rig code to control the person-specific aspects, such as identity. Then we feed the expression parameters into the decoder to get a colored mesh, and apply the poses and illuminations to obtain the per-image reconstruction. With the reconstruction, we compute the optimization energy and iteratively update the parameters. Finally, we adopt a multi-level scheme. Inside the optimization, the energy has three terms. First, a feature metric term in UV space measures the appearance consistency among views. Second, a landmark alignment term measures landmark reprojection errors. Third, a photometric term measures how well the albedo and shading reconstruct the image. With this energy, we compute the gradient with respect to rig code, poses, and expressions, and update them by gradient descent with a step size regressed by a neural network. Finally, at the end of each level, we update illuminations with linear weighted least squares. Our model is trained end-to-end in a supervised manner with standard losses. Please refer to the paper for more details. Our method can be used for 3D face reconstruction as well as face retargeting. For reconstruction, our algorithm can be applied on multiple images, videos, or even a single image. Compared to prior arts, our method is able to achieve a superior reconstruction quality, especially in terms of the geometry accuracy, which is a fundamental aspect for 3D reconstruction. When applied to videos, our method produces stable video reconstruction without any additional smoothness constraint, and also outperforms existing approaches. For retargeting, our expression tracking and reconstructed rigs reasonably transfer facial motions across different identities. Compared to the prior art, our method has superior shape quality that better reflects the personal characteristics of the target identity, such as the round chin instead of the sharp one. Thank you for watching.